Hi, in this video we will talk about continuity. Up on the board here is our definition for continuity at a point A. So, a function f is continuous at A if and only if the following three conditions are true. First condition, f of A exists, which means the value f of A has to exist. So when you plug in the value of A into the function, when you substitute that value into f of x, there should be a value. Number two, the limit as x approaches A of f of x exists. And three, the limit as x approaches A of f of x has to equal f of A. Notice that step 3 just says that the two results you get from 1 and 2 should be the same. These three rules of continuity will be tested every time you have a question that asks if a function is continuous at a point A, and that point value A will change each time. Sometimes it's 1 or 2 or 0, could be any number. So just be mindful that you want to test these three. Once one of them fails, then the function is not continuous at that point anymore. So if you start with the first one and you find that there is no value, okay, then you stop. Okay, the function is not continuous at x is equal to A. And then the same goes for all the remaining of the three rules. So memorize these three rules, and we will have a bunch of examples that we will practice. In this example, we will be using the laws of continuity, the three laws that were just previously mentioned. So example 1, show g of x is continuous at x is equal to -4. G of x is the function x squared minus 3. So in order to show if a function is continuous, you look at the three laws that were just stated in the definition of continuity. The first one, does g of that value at the point, g of A, exist? And in this case, the A is -4. So you're going to substitute -4 into the g of x function. So g of -4 is equal to -4 squared minus 3, 16 minus 3, which is 13. So the first definition of continuity, the first piece, exists. Now let's look at the second law. The second one says, does the limit as x approaches that A, the A here is -4, so you plug or substitute the -4 into A of g of x. Now we think back to the ways we evaluated limits algebraically. You first try to substitute the A value into the function. If you get a result, then that's your limit. And we get 13. The third law of continuity, does the limit as x approach the A value, which in this case is -4, of the function x squared minus 3, does that equal to g of -4? It does. So you just want to now state right underneath the limit as x approaches -4 of x squared minus 3, what does that equal to? We'll look at 2. So you put that here, 13. And what does g of -4 equal to? That's 13. So it's true. Therefore, these three little fancy dots means therefore, g of x is continuous at x is equal to -4. So every time you're asked to show if a function is continuous at a point, you need to do these three steps. You need to show them. You need to show g of the value. Plug it in. Show your result. You need to show the limit as x approaches that value of the function. And use your techniques of evaluating limits that we had previously practiced. And thirdly, you need to show that they're equal. This statement is extremely important. We need to see that. That needs to be present on your paper. You need to show the limit as x approaches the A value of the function is equal to the function with the value inside. So be mindful that this is always the A, this is always the A. Students mix that up sometimes. They're not sure what to place here. X approaches the A value. And then in your final statement, make sure you state what your result is. Now, what if a function is not continuous at a point? What if one of those three rules fail that we tried before in the previous example? Well, if that's the case, we say that the function f is not continuous at the point A, and f is then said to be discontinuous at A. A is called a point of discontinuity of f. So there are many examples that we will see where a function is discontinuous at a point. And it's discontinuous because either the value doesn't exist at that point, the limit doesn't exist at that point, or the value doesn't equal the limit at that point. Overall, we looked at an example just before of a quadratic function. A quadratic function is a polynomial function. So a general rule to go by is a polynomial function is continuous at every point. And you can say that's true for every polynomial function that we have looked at. And lastly, we can say a function is continuous on its domain if it is continuous at each point in its domain. So you have to first be able to tell what the domain of a function is. And then from there, as long as it's continuous at every point in its domain, you could say that the function is then continuous on its domain. It may not be continuous everywhere, but it may just be continuous on the values that are in its domain and those values only. What we have here are the types of discontinuities that you may see. The first type of discontinuity is called a jump discontinuity. So basically what happens is the line or the function jumps. So it started here and then went from here to up and then jumped up. I always compare this to like Super Mario Brothers when they used to ride on their track and then they jump up. So Super Mario jumps up and he has to keep running. Notice here which of the three laws of continuity fail. There's a value. The value is at this point. Let's say this is continuous and x is equal to 0. There's a value at 0, but what doesn't exist is that there is no limit, because the limit on the left is not equal to the limit on the right. Remember, in order for a limit to exist, both the limits on the left and the right have to be the same. So this one fails the second law, because the limit as x approaches 0 of f of x does not exist. And that's very important. So if you're asked a question, is this function continuous at 0, you would say no, and you'd have to justify why. So you'd have to say because it fails, that the limit as x approaches 0 does not exist. Now let's look at the next type of discontinuity, and those are removable discontinuities. Removable discontinuities can be represented in two different ways. Firstly, if you notice, it really continues, like the line is connected, the function is connected, however, there is a hole in one of the spots, and there is no defined value at that point. So this graph of the removable discontinuity fails because there's no value at A. In this case, A is also 0. So this fails the first law, and you have to state f, it's g here, so g of 0 does not exist. ZNE does not exist. Now if we look at the second example of removable discontinuity, same picture, right, except it has a value. The value is defined here. And let's say that value is 1. Y is 1. I don't know if you can see. There you go, the value is 1. So if that's the case, there is a value, great. There is a limit. Let's say this limit here is -1. There's a value, there's a limit, but what's not true is that the value doesn't equal the limit at x is equal to 0. If I were to write this out, f, it's h, so h of 0 is 1. The limit as x approaches 0 of, we're dealing with h here, sorry, of h of x. The limit as x approaches 0 of h of x is -1. That's rule 1, that's rule 2, but look at rule 3. Rule 3 says, well, do the two values, are they the same? So does the value at 0 equal the limit at 0? No, right? Because the value at 0 is 1, the limit at 0 is -1. So this fails because the limit as x approaches 0 of h of x does not equal h of 0. The statement is very important, the statement that says that it fails. So this statement right here is really important. Again, notice that the value at 0 is 1. The limit at 0, where the left and the right hand side meet, is -1, but they're not the same number. So therefore, it fails to be continuous, and that's a removable discontinuity. Note that it's called removable because we actually could redefine the function and fill in the hole. Or we could redefine this function and take that out and then fill in that hole. So it's a manipulation. And later on we'll talk about how to make removable discontinuities continuous. But right now you want to be able to find out why it's a discontinuous function. The next type of discontinuity is an infinite discontinuity. Here are two examples of infinite discontinuities. What happens here is that the limit as x approaches, in this case and in this case 0, from both the left and the right, are some form of infinity. So as x approaches 0 from the left, it approaches negative infinity. As x approaches 0 from the right, it approaches positive infinity. Here, as x approaches 0 from both the left and the right hand side, it approaches positive infinity. But it's an infinite discontinuity. And the last type of example you will see is an oscillating example. These aren't as common, but this just means, if you notice, oscillating means it goes back and forth, kind of like a pendulum. But what happens here is right in the center, it's so condensed that no matter how much you zoom in, zoom in, zoom in, it's always going to be infinitely oscillating in the origin, in this example in particular. So you can't state what's happening, where the limit is. When we talk about discontinuities, a good key way to always graphically figure out if a function is discontinuous is to ask yourself if you need to pick up your pen to draw the picture. If you need to pick up your pen, then the function is discontinuous. So, for example, here, I need to pick up my pen to continue drawing it. Picking it up means it's not a continuous function. Think about the word continuous. Flows, continues. I can't do that here. I have to pick up my pen. Similarly, here, I have to pick up my pen, jump over that hole, and then keep drawing. Here, same thing. I got to pick up my pen, draw the dot, and then continue drawing. As well with infinite, I have to pick up the pen to draw both of these infinite ones. I need to pick up my pen. And oscillating, it's just really hard for you to even figure out what's happening there. So these would be examples of discontinuities. The most common ones will be everything but the oscillating. That one's not covered as much in the questions that we will see, but the other ones are very common.